Hello, welcome to the third video of A-Level Computer Science. In this video, we are going to talk about internal coding of numbers. Have you ever used this calculator in math or in physics? It is very smart, isn't it? But how does computer represent negative numbers? We learned previously that inside of a computer system, computer uses binary, and we know how to convert a number, a positive number, to its corresponding binary. So today we are going to learn how computer represent negative numbers. Before we start, I have two quick questions to test your knowledge about what you have learned previously. The first one is, how many different numbers can be represented with an 8-bit binary? Oh. So think about it to see if you can solve this problem. Alright, here's the answer. So suppose you have 8 bits, then the unique combination is 2 to the power of 8, which is 256. So how do we get there? Suppose we only have one digit, one bit, and then it can only be either 0 or 1. And this is two combinations. If we have two digits, the upcoming digit, this one, can form a unique combination with each 0 and 1 of this digit. So we have 0, 0, 0, 1, 1, 0, and 1, 1. So each 0 can make a new combination with the previous 0 and 1, and each 1 can make a new combination with the previous 0 and 1, which means it doubles. So it's 2 times 2, which we have 4. So what about 3 digits? So when we have 3 digits, each 0 can make a unique combination which we have done previously, and each 1 can make a unique combination with which we have done previously. So which means that the number will double again, which is 8. So suppose we have n digits, the number of different unique representations will be 2 to the power of n. So in this way, we have 8-bit binary, and then it will be 2 to the power of 8, which is 256. Okay, and the other question is, what is the largest value of an 8-bit integer? I think this one, hopefully, is a bit simpler than the previous one. I hope you get the answer at the moment, and let's see. So the largest value of an 8-bit integer is if we feed all of these 8 bits with 1. Yeah, so this is the largest 8-bit integer, and we just need to convert this number into binary. So we put 1, 2, 4, 8, 16, 32, 64, and 128. And we all got 1, so we just all add them up. Okay, and I do a special trick here, and the number will be 255. Let's see if it's correct. Yeah, it's 255. There is another way to calculate this. We know these numbers are all 1, and suppose we add 1 to this number. So I will clear what I have done previously. So we remember the largest bit is 128. And we plus 1 to it. As this is binary, when a digit reaches number 2, it will increment by 1. So 1 plus 1 is equal to 1, leaving 0. So 1 plus 1 is 1, 0. 1 plus 1 is 1, 0. Blah, 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 blah. So these will all be zeros as we increment by 1 each, and with a leading 1 here. So this number is quite easy to solve. It's just we double the 128, which we get 256, or 2 to the power of 8. And then we just minus this 1 back because we add 1 to the original number. So 256 minus 1 is equal to 255. And this is how I arrive to this answer. Okay. So today's question is about representing negative numbers. So for positive numbers like 6 plus 6, it can be stored as an unsigned integer in binary like 110. So this is 1, 2, 4, So 4 plus 2, which is 6. But what about how to store the minus 6? Well, this is a question we're going to discuss today. Well, there is an interesting story about why I choose the number 6, because in China, some people put the number 6 on the window and the police come. Why? Because 6 in China represents a binary number sequence of 110, and 110 is a police emergency number in China. So the police thinking that the person in the house needs help. So they just come there and check. This is why I think about the number 6 and an interesting story about it. Well, let's come back. So how do we store minus 6? The simplest way is to add a sign bit before the digit, the binary representation of 6, which is 110. So we can have 0, 110, we represent this as a positive 6, and with 1110 as minus 6. And this introduces a sign and magnitude representation. So sign means they have a unique sign bit. When it is 0, it is positive. When it is 1, it is negative. And the remaining 3 bits represent magnitude. However, this problem has a really interesting problem because it will have 2 zeros. It has one positive 0 and one negative 0. However, we know that we only have 1 0, which is not either positive nor negative, so this could introduce some problems for the calculations. Another thing is that we can see obviously for positive numbers 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1 is all incremented by 1. However, for the negative digits, we know when minus 2 plus 1 is minus 1. However, when minus 2 subtract 1, we got minus 1 here. If we think about pure binary, so for example, 1001, if we plus 1 to it, we get 1 plus 1, 1, 0, so it's 1, 0, 1, 0, which means that it is a plus 1 in this direction. However, for pure mathematics, we know that it will be a plus 1 in this direction. So I will summarize here. For negative numbers, numbers are incremented in the opposite direction. So this is the reason why this method is not really good. So do we have any other methods to solve this problem? Well, the answer is yes. So we introduce another method called 2's complement. Another way to do this is to use the 2's complement form. To find the 2's complement form of an integer, we first need to find its 1's complement. Okay, so how do we find the 1's complement? If all bits in a byte are inverted by changing each 1 to 0 or each 0 to 1, we have formed the 1's complement of the number. In another way, if this bit is 1, we invert it to 0. And if this bit is 0, we inverted it to 1. So for example, to represent minus 6, the first step will be 6, converted to binary, which is 0, 1, 1, 0 directly, and this is positive 6. Then we have the 1's complement by inverting each bit. So 0 changing to 1, 1 change to 0, 1 change to 0, 0 change to 1. So here, 1001, we got the 1's complement of 6. And then we need to get the 2's complement. The 2's complement is very simple after we have the 1's complement. So 2's complement is equal to the 1's complement plus 1. So 1001 plus 1, we have 1010, which is the 2's complement of 6. This is how we represent the number minus 6. So let's summarize the process here. In order to find minus 6, we first convert 6 to its corresponding positive number, 0110, which is plus 6. Then we do the 1's complement by inverting each digit. We get 1001. Then we plus 1 to the 1's complement. So 1001 plus 1 is equal to 1010. So plus 6 is 0110 and minus 6 is 1010. You'll probably notify that the positive number has a leading 0 in front of it, and a minus 6 has a leading 1 in front of it. What does this infer? This infers when we're doing this conversion, we automatically add a sign bit to it, without actually knowing it. The 2's complement is a method for representing positive and negative integer values in binary. The useful part of the 2's complement is that it automatically includes a sign bit rule. To form the 2's complement, add 1 to this 1's complement. So which means that this can really help us simplify the process, because we don't need to think about, oh, we need to add a sign bit in front, but it actually did automatically. So you can try yourself with numbers +7 and -7 with 4-digit binary representation. You can pause the video here if you think you need longer time. Okay, I suppose all of you got the answer, and now let's go through the step with me. So the first step is still find +7 +7, which is 1, 1, 1. And in order to find -7, we flip each bit first, 0 to 1, 1 to 0, 1 to 0, 1 to 0, and then +1. So we got 1001. Did you get them all correct? I hope so. Okay, and there is also a quicker method for the conversion. The previous method, we need 2 steps. We need to flip each bit first, and then add 1 to it. There is a quicker way to do this, is that we only need to do it once. So the trick is, start at the least significant bit. So we start from the least significant bit, which is the right-hand side. Then move left, ignoring any zeros up to the first one, which is also ignored. So we copy down this 0, we copy down it here, copy down the first one, which is also ignored, so we copy down the first one here. Then the remaining bits are going to do something, right? Any remaining bits hasn't changed from 0 to 1 or from 1 to 0. So the remaining bits, we are flipping around. So for example here, 1 will change to 0, 0 will change to 1. So for this one, all the zeros starting from the least significant bit, we directly copy downside. The first one, we also copy down, which is in the color of red. And then we flip around the numbers in yellow. So 0, 1, flip around to 1, 0. We can check if the same trick applies to the +7 as well. So starting at the least significant bit, finding the first one, okay, we copy the 1 down, it's ignored. Then any remaining bits are flipped around. So 1 to 0, 0 to 1. And then this is how we get it. You can use either method, and depending on which one you feel more confident with. Okay. So we're going to see the interesting properties of the 2's complement. So first, we're going to see what will happen if we take the 2's complement again of a -7. So previously, we take the 2's complement of a +7, which is a positive number. But here we try to do the same trick on a minus number, a negative number, to see if the thing is the same or different. So we have -7 is 1001 based on previous exercises. The first step is to flip it around, so we have 0110, which is flip all the digits around, and then we +1 to it. Okay, we seems to get a positive number, but how large is it? Well, let's sort it out. So the first, this is 1, this is 2, and this is 4. So 4 plus 2 plus 1, we have +7. Wow, interesting. So we take the 2's complement of +7, and then we get -7. And then if we take the 2's complement of -7 again, we get +7. This implies an interesting property here. The 2's complement values are self-complementary, which means that if you take 2's complement of a positive number, you get its corresponding negative number. If you take the 2's complement of a corresponding negative number, you get its positive number. So for example, if we take 2's complement of +7, we get -7. And if we do the same thing again, we will come back to +7. This property is called self-complementary. And this is why one of the reasons why we use this 2's complement form rather than the sign and magnitude form. So in the exams, you'll probably be asking a question about how to convert, if we know a 2's complement number, how can we convert it back to its corresponding binary? So for example, we know it's 0, 1, 1, 1, how we can convert it to 1, 0, 0, 1, and if we know 1, 0, 0, 1, how can we convert it back? I think you can think about this question. It's very interesting. Okay, so I'm going to review the method, and the method 1 is from definition, which is probably what you're thinking of. So we know that when we have 6, we do these steps, we get the 2's complement. So what we do if we want to get the corresponding binary is just revert all these steps. So we know this is 1, 0, 1, 0, and then we minus 1, we get the 1's complement by minus 1, and then we toggle each bit. So 1, 0, 1, 1 will change to 0, 1, 0, 0, and 1, 1, 1, 1, and then we change it back to binary. This is basically we get this from the definition. However, it will be slightly hard to do this because minus 1 is not that easy to find. And after toggling, we still need to find the corresponding binary as well. Is there any method that's faster? Well, the answer is yes, this is a method too. Based on a previous property we talked about a couple of slides earlier, we say if we take the 2's complement of a minus number, we will get its corresponding positive number. So for example, minus 7, if we take it again, we get plus 7. So we can use the same trick here to convert the number from minus to plus. So for example, we have a number 10110001. Then we're using the trick that we taught previously. Starting from the lowest significant bit, find the first number, ignoring all the zeros, but no zeros, so let's just moving on. And the first one is also ignored, so we put a 1 here. Then we flip around all the remaining bits. So 0, 0, 0 change to 1, 1, 1, 1, 1, 0, 1 change to 0, 0, 1, 0. And this is how we get here. Then the next thing is, this is a corresponding positive number of this minus negative number. So what we do is we convert this number to binary and then add a minus sign. That's it. So for this one, it's 1, 2, 4, 8, 16, 32, 64. So which is 64 plus 8 plus 4 plus 2 plus 1, and then you get 79. And then you add a minus sign here, so you have minus 79, which arrives the same answer as what we have done previously. Let's check it. Yeah, this is also minus 79. And this is minus 79 as well. The textbook introduced us another interesting method, which I call the method 3, which is quite simple as well, but a little bit different from what we had talked previously. So sum the individual place values, but treat the most significant bit as a negative value. So what does it mean? So all the remaining digits, they are treating as normally as normal binary. So for example, this bit is 2 to the power 0, which is 1, 2 to the power of 1, which is 2, 2 to the power of 2, which is 4, 8, 16, and so on. So we just summarize it up and get these products. But the most significant bit, we treat it as a negative value. So for example, here it is 2 to the power 7, and then we have minus 128. And then we add all these up. So minus 128 plus 32 plus 16 and plus 1. You will find it's very interestingly, we get the same value. Surprisingly, it's still minus 79. So this means that this method works as well. In the exam, you will feel free to pick up one of the methods you feel most confident with, either method 1 with definition, or method 2 with a property of self-complementary, or with method 3 here, treating the most significant bit as a negative value. Well, for me personally, I prefer method 2 because I believe it is the simplest for me. Okay, let's move on. Properties of 2's complement representation. After knowing how we can convert a plus positive number to a minus negative number, we can have a check about the properties of this. So the first one is there is only one zero. Compared to sign magnitude representation, which listed here, it has a plus zero and a minus zero. However, in a 2's complement representation, we only have a 1 0, which could simplify a lot of problems. Another one is that we say, starting from the lowest negative value, each successive higher value is obtained by adding 1 to the binary code. So for example, we have minus 8, which is 1 0 0 0, and then with plus 1, we have 1 0 0 1, which is minus 7. So this is minus 8 plus 1, we have minus 7. So we plus 1 again. 1 plus 1, 1 0, so 1 0 0, so 1 0 1 0, which is minus 6. So this is plus 1 as well. So compared to the previous cases, which we have sign magnitude representation, it will have different order, split from 0. For here, it will be plus 1 from each, and this will be plus 1 each. But here, it will be plus 1 all the way up from the bottom to the top, which is a really great properties for doing calculations. That's the reason why we use 2's complement representation. So is there any other properties of the 2's complement? Well, there is one that is basically, by your instinct, you can get it. For positive values, you can add any number of leading zeros. So for example, 0, 1, 1, 1, if we add one more 0, 0, 0, 1, 1, 1, or 0, 0, 0, 1, 1, 1, it doesn't really affect anything. You can add as many zeros as you want to a positive number. However, the question here is there any similar rule for negative integers? So we definitely can't add 0 to the front, because if we add a 0, we change a negative number with the 2's complement representation to a positive number. So we can't add zeros. But can we add 1? Let's see if we can or not. So for example, we have these values 1, 0, 0, 1, which I will use which method to do it? I will use the second method. So doing its 2's complement again. So taking this one, remaining the same, and then flip around all the previous bits. So this will be 1, 2, 4. So 4 plus 2 plus 1, we have 7. So this number is minus 7. Okay, so this is minus 7, and then we see if this one is minus 7 or not. So we use the same trick, keep the one the same, and then flip around the other bits. You probably see a little bit here because you just add one more zeros to the leading bits. So this will be 1 plus 2 plus 4, so which gets 7, so this is minus 7 as well. We see if it still works with the third number, so which we have keeping the same bits, and then flip around, and then flip around. So we have 7 as well, and then this is minus 7. Okay, you seem to find a trick. You add one more 1 here, no influence. 2 more 1s here, no influence. So we can summarize. For any negative values, you can add any number of leading 1s. So for negative values, you can add any number of leading 1s without changing its value, which is quite interesting. Minus 7. So here is a table if you want to compare between sign magnitude representation and 2's complement representation. So as we can see here, the actual form that we use in calculators and in the computers are 2's complement representations because it has only 1 zeros and all the numbers are incremented by 1, and also it's self-complementary. So because of these properties, we normally use this form to represent a negative number. Okay. So there is an interesting question, because see from the previous table, we can only represent up to minus 7 from the sign and magnitude representation, which is 1, 1, 1, 1. However, with the 2's complete representation, we can represent one more negative values. So here is 1, 0, 0, 0. How do we do this? So suppose we have the number 8, which is 1, 0, 0, 0. Then we flip it around, which is 0, 1, 1, 1, and then we plus 1 as well, and we got 1, 0, 0, 0. What is the 2's complement of 1, 0, 0, 0? It's still the same. Are you surprised by this? Well, I definitely yes. But remember, as the most leading bit represents the sign of a number, so for this number, it represents minus 8 rather than plus 8, so it's minus 8. We can check from the tables. We can represent up to plus 7 with a leading of 0, and this is with, for the most negative number, smallest number, we can represent minus 8 with a leading 1. So this is minus 8. 2's complement form. The most important reason for using 2's complement representation is to simplify the process for arithmetic calculations. We will learn more about that in the next video. If you want to look for more, just check for the next one. Okay, in summary, how does computer represent negative numbers? How many ways can you thinking of after learning this lesson today? We have two methods. The first one is called sign and magnitude representation, and the other one is 2's complement representation. In order to simplify the process of calculation, in modern computers, we choose 2's complement representation. And we will be learning more about how a computer is actually doing subtraction and addition of 2's complement numbers in the next video. Well, good luck. See you in the next video. Bye.